Hey, good morning or good evening, everyone. Hope all of you do well during this pandemic time. So both California and Oregon states issue a new building code at the beginning of this year. So this class, I want to talk about how these states adopt ASCE 716 on the seismic ground motion values, and I will talk about there may be something different. So this slide provides details for the status for the states along the west coast. So California and Oregon, they already issued the new building code, 2019 CBC and the 2019 OSSC. Both of them are effective January 1st, 2020. So for the Washington state, the original plan is they will issue the new 2018 WSBC on July 1st, 2020. This was delayed to next year, February 1st, 2021. So first, I want to share a website. This is called the OpCos. So if you click the website, basically you can find all the most current building code for different states. I think most of states building code are available here, like this one, California. So this will be the new CBC 2019. So if just for the basic use, if you go through to the chapter 16, then you go to the 16, 13, that's earthquake loads. So you can check everything related to the seismic design. So it's very, very useful and it is free. So for the 2019 CBC, here are the tables in 1613.2.3. I went through the codes, so both of tables are identical as those in the IBC 2018 and ASCE 716. You can follow my other videos to determine the seismic ground motion values. So this slide just provides a summary from 2019 OSSC. The first impression, those tables seems identical with those in ASCE 716, also the IBC 2018. However, there is a note C. It has a note there, but it doesn't have the details tell you what the note C it is. So the note C is not defined in the table below. I checked this code from other sources. It has the same issue. I'm not sure it is a typo or something else. If someone knows this, feel free to draw me a note. So I just went through the code of 2019 OSSC. So I found this. I wonder this could be the node C. So in this 13.4.13, it provides an exception to the section 21.3 ASCE 7. So the right-hand side part, they are the same. They are exactly identical as the ASCE 7 section 21.3. However, on the right-hand side, they provide an exception. So basically for side classes D and E, the values of FV may be determined use streamline interpolation between the value determined from ASCE 7, section 21.3, which is something on the right-hand side. If you have side class D, the FV value is 2.5 for S1 greater than 0.2. So then, and the value determined from the table 16, 13.2.3 in the building code. So another way is that you just use a table value and based on relative header contribution from Cascadia subduction zone. So what does this mean? So the value in the table is, as if you guys watch my previous videos, those values can only be used to calculate the TS. You cannot use that to determine your base shear coefficient. So if you don't do the site-specific response analysis as described in chapter 21 of ASCE 716, so you have to use the exception 2 in the section 11.4.8. So for that, you have to use the value, FA value in the table 16, 13.2.32 times 1.5. That's your FA value to determine the design response spectrum. So we know the FV value is determining the width of the plateau. So if this value is higher, which means the plateau is wider. So this will be substantial increase the seismic load, particularly for long period building like high-rise building. So why they have this change, this exception? So I just did some research. I found this code amendment proposal application. I will provide a link in the comments area, so you guys can read by yourself. So this proposal just say the current ASCE 7 chapter 21 reflect the long period seismic header, because in the Oregon area, particularly in the West Oregon area, as you can see in the left-hand side this picture, most of seismic header probably contributed by this Cascadia subduction zone. So subduction zone basically mean you have two tectonic plate. So one plate try to go underneath another one. So this kind of seismic zone, subduction zone, typically will generate very large earthquake. I'm talking about magnitude 8.5 to 9. So the earthquake along the subduction zone typically cause the tsunami, like the earthquake occurred along the Japan coast in 2011. So the rationale, they have this exemption. The reason for that, they try to just say, right now, the NGA WAS2 GMPE, the ground motion prediction equation, they are used to develop the seismic header. They are based on the crustal earthquake. So like the San Andreas fault, that's the control fault for the seismic header in California. So that is not aligned with the subduction zone. So in order to make the header consistent with the subduction zone, so they think the value without the 1.5 factor adjustment represent the reasonable header for the subduction zone header. So that's why they have this proposal. It seems like the Oregon state building officials accept this proposal, they make the exception as what I described in the previous slide. So let's use one real example just to tell you how to use this exemption to reduce your seismic node and have some benefit. So I just randomly select a site at Eugene, Oregon. So that's the latitude and the longitude. So then I go to the USGS seismic header website. I do the deaggregation analysis. You can check my previous videos if you don't know how to do the deaggregation analysis. So this figure just show you what are the contribution regarding to the distance to the source and the magnitude of the earthquake to the total header for this site. So as you can say, for all the sources, if you say the earthquake magnitude 8.5 and greater, those are the contribution from the Cascadia subduction zone. So you add all this, this vertical axis, you say what's the percentage of each segment. This is not this entire subduction zone. It's just one segment of that fault. So you add all them together, that will be the total contribution from the Cascadia subduction zone. So I did a calculation. So basically 91% the seismic header are from the Cascadia subduction zone. So for this side, you check the seismic header map, you get SS 0.709, S1 0.404. So just assume it's a site class D. So if you use this table value, the FV is 1.9. However, in the section 21.3, the FV is 2.5. So if you use the exemption, so what you got is you use a 91%, because 91% from this subduction zone times 1.9, and another 9% that's from other type of earthquake. So you assume that value is 2.5. So use the equation, you got a 1.95. So that's compared 2.5, you have to use, that's have some kind of significant reduction. Or if you don't do the site response analysis, if you use the exemption of 11.4.8, you have to use a factor 1.5 to times 1.9, you got 2.85. So that will make your plateau much wider compared to the FV of 1.95. So basically you use this exemption from the code, you could reduce the FV value 22% up to the 32%. So what does that mean? As what I said, this the FV value just can control the width of the plateau. So the red one is I use the exception 2 in the section 11.4.8 of ASCE 716. So that's supposed to be if you don't do the site response analysis, that's the design spectrum for this project. However, if you do the site response analysis, the chapter 21, section 21.3, and now you can do the site response analysis to, and now you can have a 20% reduction. So this one, the dark red, use FV of 2.5. So this dash blue line, as what I shown here, that's based on if you use that exemption, you consider the contribution of subduction zone, you further reduce the FV value. That will be the lower bound, 80%. So what does that mean? So if you do the site response analysis, there is a possibility, because it's the lower bound value, there is a possibility you can reduce the seismic loading from this red to this blue dash line. So just look at this period on 1.2, 1.2 or 1.3 second. That's 45% reduction. So basically, if you have a short period structure, that could be a 20% low reduction, but you have something like a high-rise building, 6, 7, or even taller, 6, 7 floors or even taller, you could have a much more than 20%. You could have a 40, 45%. That's huge. That's a lot of saving for your project. Okay, that's all for today's class. I just found this is interesting. I just want let you know, if you need any help on this or the site response analysis, feel free to contact me. Thank you.